this computer. You're allowed to take your time, honestly. Motion. If we are dealing with a position vector, this points at a thing and that thing moves around in 3D, that the terminal point of my vector. So I'm starting at the origin and I just follow this motion around. I see this little object floating through space. Then my derivatives start to represent vector quantities of velocity acceleration. And if these are vector quantities, then I can think of them at the point, originating as vectors whose initial point, instead of being the origin like R of t, the initial point will be the object itself. Let me do a two-dimensional example because it's easier to draw. So let's start with the curve in the xy plane, whose equations are t squared minus 1 comma t, x of t, y of t. And let's see what we can figure out about what's going on here. So what's that picture look like? What's the graph of that? I have a graphing calculator. Put it in parametric mode. Let's draw this sucker. If I graph that, make sure you change your window for t. You're only using 0 to 2 pi. You're only going to see part of this graph. What's your t setting at? You're in degrees. How dare you? See? Okay, my sneaky moment of anti-physics bias. If you stay in radians, then anytime you want to do something in degrees, you hit second angle, and degrees are right there. Don't ever take your calculator out of radians. Okay. If I graph this, I get a sideways opening parabola. As a matter of fact, I can see from the parametric version of it up here that the equation y is equal to t, right? Y is equal to t. So if I just substitute that in here, I get x equals y squared minus 1. That's a sideways parabola. Okay, so let me draw the sideways parabola piece that I'm looking at. Now I want t equal to 1. When t is equal to 1, What point am I at? Aha! So I'm here, which means R of 1 is here. Right.
Why did you choose Dave for that?
Yeah, it was what they gave me in the problem. That was established for me in advance. I didn't make it up, but you could do this at any point. And if you want, we'll do it at another point in a minute. This curve is oriented. Remember, it's a parametric curve, right? So which direction are we going on the parametric curve? This increases. Because I just realized I drew both ends of this like it's a parabola, and technically that's not right. We're going in one way or the other. Are we going up or are we going down as t gets bigger? We're going up because as t gets bigger, our y value gets bigger. So we're really going around this curve this way. That's the orientation of our curve. Okay, wait a minute. Just intuitively for a minute here. I'm at this dot, but I'm going around the curve this way. What direction should my velocity be pointing? It should be going this way. Well, let's check. I want to do r prime of 1. Well, that means I need r prime of t. So let me go over here. What's r prime of t? So if I put in 1, I'm going to get 2, 1. So let's draw that vector. If I draw the vector 2, 1, here's where I'm going to cheat. I don't want that vector to have its original point, its initial point at the origin. I want the initial point of that vector to be 0, 1. So that we can say the velocity is with this thing. So that means I go over 2 and up 1, over 2 and up 1. From here, there is r prime of 1. That's a tangent vector. It's not a unit tangent vector, but it's a tangent vector, yes? I know it's not a unit tangent because it's longer than 1. Okay, here's a question for you. I am moving with a velocity pointed up and to the right. But my path is below that. My path is lower. That means I'm kind of curving as I go, right? This motion is not straight line. If I'm curving, then my velocity must be changing. I have an acceleration. And my acceleration will have a change in direction to it. Because acceleration as a vector doesn't just tell me whether I'm speeding up or slowing down, it also tells me if I'm turning. What's the acceleration vector in this case? So r double prime of 1, I need r double prime of t over here. Right. 2, 0. So it doesn't matter what you plug in, you get 2, 0. That's a constant. Now again, I'm going to draw this vector with its origin at our point. But since that vector is horizontal, there is r double prime of 1. Now, I want you to imagine yourself sitting in a car on this track. I'm driving in the direction t increases. My velocity is this way, but I'm accelerating this way. So I end up on a path in the middle. My acceleration is truly perfectly horizontal. So I'm starting to curve more in the x direction, curving inward. Now, I pulled t equals 1 out of the textbook. If we picked another point, if we pick another point, I'd get these vectors in a different place. Do you want to try another one? Okay, give me another t value. It could be anything you want, because this takes all real numbers, right? Okay, so if I'm looking at t equals 3, then my position vector, r of 3, 3 squared minus 1 is 8, comma 3, r prime of 3, 2t comma 1 will be 6, 1, and r double prime of 3 will still be 2, 0. Okay, picture time. There's r of 3, out 8, up 3, 6, 1, 1, 2, 3, 4, 5, 6, up 1. There's my velocity. And here is my acceleration. Exactly. The curve continues to be in between. Again, I'm a crappy artist, but if I'm moving this direction and I want to go that way, I have to change my velocity, right? Change in velocity acceleration, I better pull sideways. And since I'm going to add vectors, my result should be in between. Now, I'm in the little car driving on this track, right? Your car does not have a velocity gauge. Your car has a speedometer. What's my speed? Speed's not a vector quantity. Speed's a scalar. But speed is related to velocity. How do I get a scalar out of a vector? Oh, I take the length. So if you want the speed, all you have to do is take the length of the corresponding velocity vector. So in our previous example, back up here, my speed would be the square root of, let's see, r prime is 2, 1. So 2 squared 4, 1, square root of 5, right? So up here, speed is the square root of 5. And down here, speed is the square root of 36 and 1, 37. Talk to me. Both yesterday and Thursday, I made mention of the fact that the unit tangent was perpendicular to the radial vector. That's not true here. I mean, it's clear that these are not perpendicular to each other. These are not perpendicular to each other. Why was I able to say that they were perpendicular previously, but they're not perpendicular here? It turns out the reason I said that is because we were dealing with the unit tangent, and the unit tangent has the same length everywhere, right? That meant that your speed is a constant. When you have constant speed, what's your acceleration? Except it's a change in direction, right? So you won't have a zero, you'll have a vector that's perpendicular. It'll change direction, but not increase or decrease your velocity. So we have two different kinds of acceleration. We have acceleration that moves me forward or backwards, faster or slower, and we have acceleration that moves me sideways. Tangential and centripetal acceleration. Separate pieces. But combined, they give me the vector acceleration. So since my velocity here is not constant, my velocity has a t in it, I know that I'm going to have non-perpendicular behavior this time. More questions? Go ahead.
Does the length of the acceleration like indicate the strength of it? Like if the acceleration is like 0, would that be faster?
It would be a larger change in velocity. So it's not faster, but it's harder, right? An increase in acceleration. Okay, I get to do physics again. What do you feel when you accelerate? Get in the car, floor it. What do you feel? That push would get harder as you accelerate faster. And that's why we do acceleration in G forces. Let me make a dramatic assumption that every unit up here is metric. Then that's, I don't know, the length of that acceleration is 2 meters per second squared. That's what, a quarter G, because a fifth of G. G was 9.8. So all I have to do is take the right ratio. But G force, acceleration force. I got to do Newton's second law. I'm jumping ahead. I promise I'll jump back in a second. Wrong pen. What's Newton's second law? A is an acceleration vector, then force must be a vector too. So there's my actual concrete connection here. It's not that it's faster, it's quite literally harder. It's pushing on you harder. More questions?
So transitional acceleration?
Tangential, right? Because part of this acceleration would be going along the direction if I projected, right? And some of it would be perpendicular to that. So if I take the projection of acceleration onto velocity, I get tangential acceleration. And if I take the perpendicular component, I get centripetal acceleration. Those two added together give me net acceleration. Find you right there. I have an acceleration vector as I move along this curve, right? Well, I've got a tangent vector here. I can use the unit tangent vector, might as well make it convenient. If I project that onto this, that's the part of the velocity that the part of the acceleration going along the tangent line. That's my tangential acceleration. The perpendicular of that is going to be going along the normal vector. That's going in towards the center of that osculating circle. So it's going centripetally. It's going towards the center. Page 874. Everything we did in this example generalizes to 3D perfectly. So if instead of doing a two-dimensional example, I did a three-dimensional example, it would be exactly the same stuff. I have one, but it's just more of the same, and my pictures suck in 3D, so I'm not going to draw this one for you, but we could do the same stuff. More questions? We can go the other way. Okay. What shape did it make in midair? A parabola. Why? Why did it make a parabola? But where did it come from? How the hell does that work? The acceleration due to gravity is 9.8 negative J. It's pointed downward, right? I'm not going to throw it again, Nora, I promise. But I launched it, didn't I? So let's assume, we'll make life easy, that when it left my hand, this is the origin. That meant that there was an initial velocity. Yes? So somewhere down here at the origin, there's some velocity vector, v of 0. At time 0 from the origin, poof. But wait a minute, if it's from the origin, that also means that r of 0 is 0. It started at the origin. Now, I don't know what that initial velocity was, do you? I also don't know what angle it left my hand at. So I'm going to make my life easy, and I'm going to say that at time 0, we had some angle and some length. We had a speed of v. We'll even go ahead and call it v naught, right? Write that as the length of, get rid of this absolute value over here. It should be over there. That was my initial launch speed, and it had some angle. And again, since I was throwing it in front of me, I know that that angle is going to be in the first quadrant. So it'll be somewhere between 0 and pi over 2. So I launch my particle into the air. That velocity can be turned into a vector. Because all I have to do is I have to figure out the horizontal component and the vertical component, right? It's got some length and it's got some angle. I use my trig functions again. V of 0 is length cosine theta in the I direction plus length sine of theta in the j direction. Okay. I have an acceleration. I have the velocity I know at one point in time. I have the position I know at one point in time. How do I get the velocity equation? I have acceleration. How do I get velocity? I do the integral. And since I have a constant, I can solve for the plus c. V of t is the integral of a of t dt. Well, that would be minus 9.8 t j. Just integrate that, integrate a constant, you get constant times t, plus c. But I know that when I put in t equals 0, this piece is going to be 0, and I'm going to get that out. So this is the value of c. I have two pieces that have j in them. Let's put those together. I now know the speed of this object and the velocity of this object at every point in time in its flight. How do I get position? Integrate again. You have velocity. To get position, you integrate again. R of t is the integral of v of t dt. What do you get? Here, but I also get these, right? I'm integrating, so I get number times t I plus number times t minus 4.9 t squared j. Aha! I have a quadratic term and a linear term. Ready for the fun part? I have a quadratic term and a linear term. It made a parabola. I have a quadratic term and a linear term. It makes a parabola. The reason projectile motion is parabolic is because the parametric equations are quadratic. But wait, there's more. Because these are parametric equations, I can really think of this as x of t and y of t, right? So x of t is number cosine theta t, and y of t is all the rest of that garbage. Now, I will freely admit to getting lucky. When I launched my keys out of my hand, they landed on the table. They didn't go out the window. They didn't hit the floor. They hit the table. Question. The picture I drew launched the item from the origin. If that is the ground level, then I'm going to hit the ground out there somewhere. Where? How far will this object go? Right. And when it hits the x-axis again, what do I know about the y value? Aha. So in order for me to figure out how far this thing goes, first I need to know when it hits the ground. And it hits the ground when y is 0. That's a quadratic equation. It's going to hit the ground twice. But if you look carefully, you'll notice that one of the roots of that equation is 0. Because I can factor out a t. So my object is on the ground at time 0, and it's also on the ground when this other thing is 0. So let's solve for t there. And I agree, this is starting to get nasty because it's all in variables. We don't actually need numbers here. I just need to figure out what time this is in terms of my starting velocity and my starting angle. If I move that to the other side, I get V naught sine theta equals 4.9 t. So I have to divide, I get t equals V naught sine theta over 4.9. That tells me when I hit the ground. How do I figure out how far I went? I want an x value. How far did I go? Plug this into x. V naught cosine theta times t. I just put the t in. I have two V naughts. They're being multiplied. I have V naught squared. I have cosine theta, sine theta over 4.9. Where'd the 4.9 come from? Oh, right. We took gravity was 9.8. We ended up dividing by 2, right? I'm going to be sneaky here. I'm going to multiply by 2 on top and 2 on bottom. Because now on bottom, I have 9.8 V0 squared. And on top, I have 2 sine theta cosine theta. All of a sudden, in the back of my head, an alarm goes off. That's a trig identity. 2 sine theta cosine theta. almost. Sine of 2 theta. Okay, if you're going to launch something and an ideal object, you want it to go as far as possible, what angle should you launch it at? What angle is going to make this as big as possible? What's the biggest value you can get for sine? 1. Sine of what is equal to 1? Pi over 2. So I want 2 theta to be pi over 2, which means I should launch it at pi over 4. The biggest possible distance you can go is at an angle of 45 degrees. This, by the way, is formally written down as the range of a projectile. Now, please note that this does take the universe and make it a lot simpler. There are 2 things that I'm ignoring here. I'm ignoring any difference in elevation between me and the target. I assumed that I was at a height of 0 when I launched it, and the target was at a height of 0 when I hit it. I'm also ignoring wind or air resistance or any other type of behavior like that. The reason the damn thing moves in a parabola is because I have a quadratic equation. And I can maximize that quadratic equation perfectly by doing nothing more than simplifying the trig function involved. If you raise your angle further, you end up shrinking because you're going too high. And if you lower your angle, you don't get high enough, so you hit the ground early. But really, that's all I've done. Launch my particle at some given angle. By the way, if you change 9.8 to some other number, 1.67, I believe. If you use 1.67 instead of 9.8, that's the gravitational force on the moon. You can do this exact same calculation there. You replace 9.8 with 74 something or other, and then you're doing this on Jupiter. You replace it with 9.1, you're doing this on the surface of Mars. I don't care what planet you're working on. As long as I neglect the atmospheric behavior, this is exactly what I need. Ladies and gentlemen, I give you everything you've ever caught in your entire adult life. Every basketball shot you've ever made. Only now I have to adjust for the difference in your height and the rim, right? How high is the rim? 2.5 meters? 10 feet. So 3 1/3 meters. There we go. But you're about 1.5 meters tall, so I can use 1.6 meters and then I can make the adjustment. But then I would change R of 0 to be negative 1.6 so that I knew I wanted to be up higher. We do this intuitively. There's a lot of calculus going on in your brains all the time. Original tank gunners. When you launch a shell out of a tank, it's following that motion. So what do you have to take into account? Wind and elevation differences. And any old war movie you watch, what's the range to target? What's the elevation? What's the windage? That's what they're doing. They're adjusting based on a book that's already done the calculus for me. They're looking it up to adjust the angle appropriately. Objects in free motion, only under the influence of gravity, obey this rule perfectly. The longer the distances get, the less I can use this. Why? Even ignoring all the other forces, ignoring the air, ignoring drag, ignoring wind. What's the problem when I try and take a really long shot, like 2 or 3 miles? The world stops being flat in between us. And I have to worry about the curvature of the earth. I'm sorry? Oh, yeah, of course. The earth is flat. If I am 6 foot tall and you are 6 foot tall, and we are standing 5 miles apart, even assuming we had perfect line of sight and binoculars, you wouldn't be able to see me. I'm over the visible horizon to you. You can't see around the curve of the earth to me. 6 feet to 2.5 miles. That's the curvature of the earth. That's why it looks flat. Because very few of us can see 3 miles in any given direction. On the other hand, I drove through Kansas. And Kansas City has this wonderful problem that as you drive up on Kansas City, you can see Kansas City from about 150 miles away. Because you see the skyscrapers, but the world is flat. No, the earth isn't flat, but it sure looks like it because you can see that thing and it's so far off because you're looking up and ignoring the curvature of the earth. This same behavior can be adjusted to take that change in height into account. I have to aim like my height on the far end is negative. Just like I did with you, Mia, adjusting for the height of the basketball rim. I give you the intercontinental ballistic missile. You throw it in the air and it just kind of goes, whee, splat, and lands on the far side. I can go a step further. And I can say that as long as gravity is the only force I'm working under, these tangential and normal components of my acceleration define my path of motion uniquely. Johannes Kepler, 1687. The planets move in elliptical orbits with the sun at a focus. So during the summer, when this side of the planet is closer to the sun, actually moving faster at aphelion than we are when we're out at the far end at perihelion, when we're further away from the sun. Now, the difference between the aphelion and perihelion of the Earth is not huge, but it literally means that when you are closer to the sun, you're moving faster, much faster. The line joining the sun sweeps out equal areas in equal time. So from here to here, when I'm further away, is slower than when I'm closer because the area has to be proportional. So your speed changes by the square root of that distance behavior. The square of the period is proportional to the cube of the length of the major axis of the orbit. So we can measure period and orbital behavior just by looking at how long it takes a planet to move. We figured out how long it took Jupiter to go around the sun by watching it move through the heavens, and that was what we used to figure out how far away it was. These came about because between the years 1200 and 1700, there were hundreds of observatories built in Arabic-speaking nations. The rise of the Ottoman Empire. People, we launched a probe towards Mars. How's it getting there? We launched one out towards Titan around Saturn. How's it getting there? It's going to whip around other planets. And as it moves close to those other planets, the gravitation will pull it faster and faster and slingshot it around. And that slingshot move works because of this. We got Apollo 13 home because of this. I will never get to the stars. This is never going to be a pilot, people. But I can do this. And if I can do it for an imagined object, I can do it for a real one. And I might not be able to put me on the surface of Titan. Maybe your grandkids will get there. Maybe one of your kids will be sitting in that lunar colony waiting for their next spaceship to Mars. I don't know. That's how we're going. And the only thing it depends on is being able to integrate. I am a horrible, horribly cynical person. I need the other tab. Where's my other tab? There it is. John Gillespie McGee Jr. was a pilot. And he wrote this amazing poem about what it feels like to fly. I'm never going to do it. But in my mind's eye, I can quote him. I have reached out my hand and touched the face of God. I know exactly what that motion is. I know how to get there. I know how to do this. I set myself free from the shackles of earth. People, this is power. And it's between your ears. All you have to do is integrate. Told you I had to teach this section. I had to switch Friday and Thursday because I had to teach this one. So tomorrow, I sent you all an email earlier today with an invitation to the teaching demo, 1020 across the hall in Mara 333, with a survey link for the teaching demonstration. If you come, please come. If not, I understand. But I will obviously be at other things. My office hours will be extended in the afternoon to make up for us not having a question and answer day. So come bug me with whatever questions you have for 13.2, 13.3, 13.4 tomorrow afternoon over in the Enrichment Center. If you can't make that, start emailing me. I will see you all on Monday, or at least tomorrow. It's teaching demo.